Let's look at the exercise questions, which is the practice questions on the graphs of chemical equilibrium. Now it says this question 1 and question 2 refer to the following equation, right? Which is this question and this question. A chemical reaction represented by the following equation reaches equilibrium in a sealed container. Right, we have those hypothetical reaction, which is X in solid state and YZ in aqueous, and then that product and that product. We know this one, the solid, doesn't affect equilibrium, right? Now, the question it says, now the statement it says the rate of forward and reverse is indicated on the graph below. So this is a graph of rate and of rate. Of forward and reverse reaction. Now, if you're looking at this graph, we have time there. The graph started reaching equilibrium at 5 seconds, right? From 5 seconds up until 15 seconds. At 15 seconds, there was a disturbance there. But if you're looking there, both the rate of reverse and rate of reverse and forward are equivalent, and they're increasing at the same time, right? They're increasing at the same amount, not at the same time. They increase at the same amount there, and then it reaches equilibrium there. So when both increasing at the same amount like that, we should know it's the what? It's the catalyst that was added there. Now it says what was done at 15 seconds to change the rate of reaction as indicated on the graph. So the catalyst was added. So the catalyst was added there. The temperature was decreased, no. And the surface area of that, no. And the external pressure of the reaction was decreased, no. So the correct answer there, it's A. The catalyst was added at 15 seconds there. Let's go to question 2. Question 2 is referred to this type of reaction. What was done on 20 seconds, and it refers to this graph. What was done in 20 seconds to change the rate of reaction as indicated in the graph? See here, whatever that was done, it is a decrease there. Whatever that was done, it is a decrease. So it can be a decrease in pressure, it can be a decrease in concentration, it can be a decrease in temperature. There is a decrease there. So what was done in 20 seconds for the rate of that? A negative catalyst was added there, no. A temperature decrease, that's correct. There could be a temperature decrease. A surface area decreased there, no. An external pressure of the reaction increased there. So the answer there is B. There's a temperature decrease. Question number 3. It says a pure hydrogen iodide is placed in a sealed container, right? When it says in a sealed container, that means it's a container where you cannot add anything on it. Now, the hydrogen iodide react as the following, right? We have hydrogen iodide that decomposes to hydrogen and iodine, and delta H is greater than 0. That means the forward reaction is endothermic and the reverse reaction is exo. Right? It says equilibrium is reached after 8 minutes. If you look at this graph, sorry guys, if you look at this graph, the rate were different, and then at that time, which is at 8 minutes, that's when the rate of forward and reverse at 8 minutes, it's when the rate of reverse and forward are equal, which is it reaches equilibrium. And for the next 2 minutes up until at 10 minutes there was a disturbance there. At 10 minutes there's a disturbance. Let's look at that. A sudden change in condition causes the rate of both forward and reverse reaction to increase by the same amount. So at 10 minutes, this change, there's an increase in both rate of forward and reverse by the same amount there. The reaction can be expressed by the following graph of rate of reverse reaction. The 10 minutes, it says the change after 10 minutes could have been caused by? What could be the cause of this one? Right, guys, it's very important when they say it in a sealed container. In the sealed container, guys, there's no change in concentration because it's closed, it's sealed. You cannot change a concentration. You cannot change you cannot add a catalyst there. So it says here increase in temperature. So it can't be an increase in temperature, that one. That one, it can't be an increase in temperature. In this one, it can be an increase in concentration. An addition of a catalyst, no. So that can be, guys, we know the reason I'm saying it's not a temperature curve is not like this. That's why I'm saying it's not a temperature curve. It's not like this. There will be a spike and there will be a gentle if it's a temperature. So this one, it's between the catalyst and the pressure. So but it's not an addition of a catalyst because it's sealed. A pressure, you can increase a pressure of something while it's sealed. So it's between these two, right? It's between these two. You can increase the temperature of something that is sealed. You can increase the pressure of something that is sealed. In fact, you can change the temperature. You increase or decrease. You can increase or decrease the pressure of something that is sealed. So this is between these two. But at the curve, we know this curve, it cannot be a temperature. The curve of a temperature is not like that, right? So it's the pressure. So the correct answer there is what? It's pressure. So it's D. Right, I hope I make sense by that, guys. Now let's look at number 4. Question number 4. It says a decomposition reaction of hypothetical AX3, which is a hypothetical. It's not chemicals that exist, guys. It's just something that it's an ideal. It's hypothetical. That in a gaseous state, which is represented by the equation, first reaches equilibrium in a closed container at a temperature T1. Right? Okay, so this is temperature T1, guys, when it reaches the equilibrium. And then where there's a disturbance, it's temperature what? T2. So we should know when we refer to temperature T2, it reaches equilibrium in a closed container in T1. So it reaches the equilibrium here. It reaches the equilibrium at T1, right? Now here's the reaction. It's a homogeneous equilibrium there. It says when the temperature is increased, the system regains the equilibrium at T2. Right, so here, guys, they tell us that there's a temperature increase and then it regains the equilibrium there. So there's a reinstatement of the equilibrium there. Now it says the changes of the rate of these reactions are represented in the graph. Which one of the following statement is correct, guys? Very important here. The broken line represented the reverse, and the solid line represented the forward. So at T1, the rate of forward and reverse are equivalent. But at T2, when the temperature is increased, if you see here, the forward reaction is what? Is favored, right? So if the forward reaction is favored, that means the product of these are increasing. That means the Kc, what? The Kc increases. Let me write it. So at T2, let's look at T2. At T2, forward is what? Is favored. The forward is favored. Forward is favored. How do we see the forward is favored? Look at the solid line is favored. It increases more than the reverse. So forward is favored here at T2, right? That's important. But at T1, which one was favored there? At the T1, the one that was favored at T1, guys, there at T1, if you look at there, the forward was decreasing and the reverse was increasing, right? And the reverse was increasing. So at T1 there, at a T1 as it starts the equilibrium. Okay, let me finish by saying here at T1 the forward was favored. So if forward is favored, guys, that means the product will increases. So if the product increases, that means the Kc will be greater than 1, which is the Kc will be bigger. But now at T1, the reverse was favored. The reverse was favored, and the Kc is what? Is less than 1. So if Kc is less than 1, that means the reverse is favored, right? So now it says here, which one of the following statement is correct? And another thing, guys, here they said the temperature has been increased. So the temperature increases favors endothermic reaction. So the temperature favors endothermic reaction. So here they say endothermic reaction. So that's not endothermic reaction. That's exothermic. That's not exothermic reaction because increase in temperature. The increase in temperature favors endothermic reaction. So the answer is between these two. Let's hear. Endothermic reaction, that's correct. Now it says, let's take it to show it's correct. Kc at T1 is less than Kc at T2. Yeah, that's correct. Look at T1, the Kc is less than 1. At T2, Kc is what? Is greater than 1. This is correct. But let's look at another one, just for the benefit of the doubt. It's an exothermic reaction. Kc at T1 is greater. The Kc here is not greater at T1, is greater than Kc at T2. The Kc here is not great, it is greater than the Kc here. So this is not correct. So the answer here is C. There's no question 5, guys. Let's look at question 6. Now it says here, exactly 5 mole of XY3 gas is placed in an empty container of a volume of 2 cubic decimeter, which is then sealed. The following reaction reaches at equilibrium at 400 Kelvin, which is the temperature. We have the decomposition of that to that to that. It's a homogeneous equilibrium. After 8 minutes, the temperature is lowered to 300 Kelvin. It's very important, that statement, that the temperature has been lowered. So we know at the back of our mind, the temperature, when we lower the temperature, exothermic reaction is favored. It's very important to keep that in mind. So the temperature has been lowered after 8 minutes. So let's look at our graph. Our graph is at equilibrium at 4 minutes, and then it continues to be at equilibrium up until the 8th minute. At 8th minute, the temperature has been lowered. So if the temperature has been lowered, look at, this is reverse and this is forward. Look at the forward decreases more and the reverse decreases less. So here the reverse has been favored. Reverse is favored. Right? Reverse is favored. So we can conclude from this graph, since the temperature has been lowered, the reverse has been favored. So this simply means that the reverse the reverse is what? Is exo. Right? So the exo is what? Is reverse when we lower the temperature. Where do we get that? The theoretically decrease in temperature favors what? The exo. Right? And then we see that the reverse here is favored. So the reverse here is favored because it decreases less than the forward. So that means the reverse is favored, and the reverse is what? Is exo. Right? And then it says the graph shows the change in the reaction against a total lapse in 12 minutes. And then in 12 minutes here, there's a change there. Right? Okay, let's answer the questions. 6.1, it says, which reaction, forward or reverse, is represented by the dotted line? So the dotted line, guys, they represent the reverse. That's not always the case. But since the initial, it starts from 0, the reverse always start from 0, right? So the reverse start from 0 always. So the one that starts here is the reverse. So the dotted line is the reverse. Okay. Now 6.2, it says when does the reaction first reaches equilibrium? It reaches equilibrium here at 4 minutes. In 4 minutes. Right? Now in 6.3, it says, is the reaction represented by the dotted line exothermic or endothermic? Explain your answer. Right? I think I've explained the answer when I was explaining what happened there. So, it says, is the dotted line exothermic? The dotted line, guys, here in 6.3, the dotted line, it has to be the exothermic. So the reverse, we can say reverse is reverse reaction. Let me write reaction. Reverse reaction is exothermic. Right? Why am I saying it's exothermic? That's the explanation that I gave you here. At 8 minutes, right? At 8 minutes, there's a decrease in temperature. Where do we get that? There was a temperature lowered, even though they did not tell us there, but we can see there's a lower, both the rate of reverse, they decrease there. So guys, so there in explaining, we can say um, both decreased, which is the rate of reverse decrease because because um, because a decrease, there is a decrease, right? A decrease in temperature, a decrease in temperature decreases all reaction rates. So that's important, right? Now we can say the dotted line did not. It's very important to look at the dotted line. At the dotted line, what happened to the dotted line there? The dotted line, it did not decrease as much as a solid line. I've already mentioned that if you look at the solid line decreased more there, and the dotted line, it did not decrease as much as the solid line. So let's continue explaining. What does it mean? Which implies that the rate of reverse is higher than the rate of what? Than the rate of I said reverse, than the rate of what? Forward. Right? I think that makes sense, guys. I think that makes sense. Now let me end with that. Now reverse reaction, that's important. Reverse reaction is exothermic. Reverse reaction is exothermic there, due to lowered or decreased temperature. Right? It's very important, guys. That's an explanation. Do you see? It's 5 marks. It's very important to explain that. Okay, let's look at number 7. Number 7, it says an amount of sulfur trioxide is sealed in a container at 400 degrees Celsius. and the following reversible reaction takes place, right? Now it says the graph shows how the reaction rate measured from the start of the reaction change with time. So we have this reaction rate graph here. There's a disturbance in 10 minutes. After 10 minutes, right? It says state and give reason whether the forward reaction whether the forward reaction above is homogeneous or heterogeneous. So this reaction, guys, since their state, it's gases. So the answer here, it will be homogeneous. Homogeneous, right? It will be homogeneous. And the reason for that, you say all substances are in the same phase, i.e. gases, right? They are in the gases, in the gases, right? 7.2, write down the equation for the reaction that indicated by the dotted line. This, guys, is very important. There's 7.2. The dotted line here, guys, the dotted line is the what? Is the reverse, right? Dotted line is the reverse. Dotted line is the reverse and the solid line is the forward. Now the question, it says write down the equation for the reaction indicated by the solid. I said dotted line here, by the solid. So the solid, guys, here is the reverse. So the reverse, it's from the products to the reactants. Alright. So what I can do, the reverse reaction here, guys, it says solid line is the forward, so they want the forward. So if they want the forward reaction only, guys, this is what you do. You write the same reaction, but you only have one arrow that shows forward. So I'll have the 2 mole of sulfur trioxide in a gaseous state, and the arrow that is forward, it must be the arrow with the full, not this arrow, guys, not the half arrow like that. It must be the full arrow like that. And then 2 mole of sulfur dioxide in a gas state, plus the oxygen gas, right? So that's the forward, guys, right? That's the forward. So let's say if they wanted me to write the reverse reaction, right? The reverse reaction, what I was going to say, I was going to write and say 2 sulfur dioxide in a gaseous state and plus the oxygen in a gaseous state, and then arrow, and then sulfur trioxide in a gaseous state, 2 of them. This is the reverse, guys. If you're looking in the reverse, we're going this way, right? So I wrote it that way, reverse. I hope that makes sense. Okay, this is not the answer. The answer is the one that above. Okay, now let's go to 7.3. 7.3, it says, how long does it take for the reaction to first reach equilibrium from the start? So if you're looking here, it's not at equilibrium, the rates are not equal. They start to be equal after 5 minutes. So the answer in 7.3, it's what? 5 minutes. After 5 minutes, that's when they reaches equilibrium, right? It's equilibrium, guys. It's when the lines are parallel to each other and are parallel to each other, guys, no? And when they're parallel to each other, they having the same y-axis amount. I hope that makes sense. Okay, 7.4. State what possibly could have happened to the system at the 10th minute. Looking at the 10th minute there's an increase there, right? There's an increase of whatever, but the increase here, it cannot be the cannot be what? It cannot be a catalyst, right? It cannot be a catalyst, that increase. So that increase there, guys, in 7.4, it's an increase in pressure. It's an increase. I can say it's an increase in temperature there, right? And possibly, it cannot be catalyst. So it's an increase in temperature, or it's an increase in what? In concentration there, right? Let's see which one between the two. Okay, our forward is endothermic there, right? And our reverse is exo, right? I hope you can see by that. Now, what could possibly happen in the 10 minute? Okay, so if we're looking here, guys, the rate of forward is increased, is sharply increased, and at the rate of reverse, it's just gradually increased there. There's a gentle increase there. So if we say it's temperature that has been increased there, so let's see if the temperature is increased there, increase in temperature favors forward. So if you increase temperature, guys, theoretically it favors forward reaction. So the forward reaction is what? Is endo. That's why I'm saying it favors the forward reaction, because forward is what? Is endo, and the reverse is what? Is exo. Right, so increase in temperature favors forward, and even in the graph forward is favored there. So this one is an increase in temperature, 7.4, increase in temperature. Now, but possibly it could be the concentration there, right? It could be the concentration there, but with the concentration of what? Possibly the concentration of sulfur trioxide. Let's look at it. If we increase the concentration of sulfur trioxide, if we increase the concentration of sulfur trioxide, the system will decrease it and increase the concentration of product, and then forward will be favored. So this curve this curve can mean concentration or the pressure, but guys, in any question they'll be specific with that. I hope I make sense when it comes to that. Okay. Yeah, let's go to 7.5. Why the horizontal part of the graph between the 15th and the 12th minute is higher than um, the part between the 15th and the 10th? Okay, why the horizontal? Okay, mean here and here. Okay. Okay, it means, let's read the question. The 15th, why the horizontal in the 15th minute to the 20th minute is higher than, why this part is higher than this one? I hope that question asks that. So it is higher because there are different equilibriums there, number one, right? There are different equilibriums, but these are the two equilibriums. But now, since there was an increase in temperature here, there was an increase in temperature, so the rate, okay, the rate of forward and the rate of reverse here were equal there. But now, since the disturbance at the 10 minute, there was an increase in temperature, so it increased both of rate of reverse and forward reaction. Do you see that both increase at equilibrium there? So The way to say that, um, although the increase in a temperature favors the forward reaction, the rate of all reaction increases at higher temperature. Therefore, the reaction will be faster, and yeah, that's what it means, guys. So because there's an increase in temperature here, the both reactions will be faster than before, right? Um, yeah, so guys, it's very important to note that in 7.6, how will the increase in pressure affect the amount of sulfur dioxide present in the container at equilibrium? So when we increase in pressure, theoretically, increase in pressure favors the side with the least number of moles. So the side with the least number of moles is this one. So this is 2 and this side it's 2 plus 1, it's 3. So the side with the least number of moles is the reverse, so it's going to favor reverse. So if reverse is favored, the products will increase. So if the product increases, the concentration of sulfur dioxide increases. So the answer here in 7.6 is what? Increases. Increases. The reason for that, the reason for that, let's look at it again. Let's look at it again. There's something that I'm not certain about that. It says, how will an increase in pressure um, 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 affects the amount of blood present at equilibrium? Okay, so again, when we increase pressure, favors the side with the least number of moles, right? The side with the least number of moles is this side, will favor this side. So this side will increase, and these two will what? Will decrease. So I was wrong initially. So this side will decrease, so the sulfur dioxide will decrease because it's not favored. So the answer here is not increase, it's decrease. I could sense it that I was wrong, right? And the reason will always be decrease in temperature favors the side with the least number of moles, right? Yeah, I think we are done there.